Hello friends, today we will see the lecture number 5 based on vector integration. Before this lecture we have defined under the topic vector integration, first we have defined what is the line integral and how to evaluate the line integral and exactly application of line integral to find work done from moving a particle from one point to another point on given curve. So, our circulation of a vector F bar also can be obtained with the help of line integral for a closed curve. After that, we have defined what is a Green's theorem. Green's theorem gives the relation between line integral to surface integral. Then how to apply Green's theorem to evaluate line integral. Then how to verify the Green's theorem. So that type of examples we have completed based on this Green's theorem. As well as we have defined another theorem, Stokes theorem. Stokes theorem is a general case of Green's theorem. Stokes theorem gives relation between surface integral to line integral. Then how to apply Stokes theorem to evaluate surface integrals with the help of line integral. That type of examples we have seen, and verification of Stokes theorem also we have seen for given region of integration for a function f bar, where a f bar is a vector function. Then now we will see in this lecture number 5, we will first define what is a volume integral. Now in this case we will define the volume integral like this. If a continuous vector function f bar is defined in the region R bounded by some surface S, then the volume integral of f bar in the region is given by volume V equal to triple integral f bar dv. Triple integral f bar dv. Now that will be equal to triple integral. What is f bar? F bar is vector f1i plus f2j plus f3k, and dv is dx, dy, dz. So how to evaluate triple integral? You have learned in second semester of first year in the topic multiple integrals. So evaluation of triple integral depends on the limits of the integral. If the limits are constants, then you can evaluate the triple integral with any order, with any order, first with respect to x, then with respect to y, and then with respect to z, or vice versa also. And if the limits are in terms of x or y, then we have to decide exactly the order of the integration. So that methods you have studied already. Now while using this volume integral in next theorem, we will also evaluate such type of integrals. Now we will define now what is a Gauss divergence theorem. What is this Gauss divergence theorem? It gives the relation between surface integral and volume integral. It gives relation between surface integral and volume integral. So what is its statement? That we will see here. The surface integral of the normal component of a vector over a closed surface S is equal to the volume integral of the divergence of f bar throughout the volume bounded by surface S. Is it okay? The surface integral of the normal component of vector f bar over a closed surface means normal component of vector f bar over closed surface means n bar dot f bar is equal to volume integral of the divergence of vector f bar means del dot f bar ds, where ds is dx, dy, dz. So this gives the relation between surface integral to volume integral. Now if you look at this, exactly what happens, suppose one surface is bounded by some curve Suppose this is a surface S, this is a curve C, this is a curve C, and this is surface S. S is the surface. So here normal component of this surface, this is n bar, outward normal. So normal component of surface S for a vector for a closed surface S. This is a closed surface S. Is it okay? So we can, if we evaluate this surface integral, what we will get? We will get the volume of this three-dimensional figure. Is it okay? So this type of study, or we have to see here how to use Gauss divergence theorem. Now we will go examples based on this Gauss divergence theorem. Now the theorem contains the divergence of f bar, del dot f bar, hence it is a divergence theorem and it is given by Gauss, hence the name is Gauss divergence theorem. Now see the example number 1 that I will read carefully. See here, evaluate surface integral n bar dot f bar ds, where f bar function is given as vector function 4xi minus 2y square j plus z square k, and S is the region, or S is the surface bounded by this parabola y square equal to 4x, the line x equal to 1, and for this xy plane z varies from 0 to z equal to 3. So these are the limits for z which are given to us. Now according to the Gauss divergence theorem, we can write this surface integral n bar dot f bar s f bar ds is equal to volume integral divergence of f bar dv. Now what we will do, what is given to us? F bar is given to us, so we can find del dot f bar, divergence of f bar. What is this exactly divergence of f bar? It is dot product of del with f bar. F bar is a vector, del is a vector operator, I dou by dou x plus j dou by dou y plus k dou by dou z. So if I take divergence of f bar, means derivative of this 4x term with respect to x, partial derivative, it is 4. Then derivative of this term 2y square with respect to y, it is 4y, and derivative of z square is 2z. I dot I1, j dot j1, k dot k1. So we get divergence of f bar equal to 4 minus 4i plus 2j. And dv is dx dy dz. Therefore, the region of integration, what is given to us, is now here sketched. See this figure. This is a parabola y square equal to 4x. This is a parabola y square equal to 4x. It is written here. Then this is a straight line x equal to 1 parallel to y axis. Is it okay? So surface is bounded by parabola and straight line. And if we look at this figure, x varies from 0 to 1 along x-axis, or everywhere x varies from 0 to 1. Minimum value for x is 0, maximum value for x is 1. And y varies from this point to this point. This point is on this curve. So y square equal to 4x means y equal to plus minus 2 root x. So y varies from minus 2 root x to plus 2 root x. Like this. And z is given already, that z equal to 0 to z equal to 3. So these are the limits for integration. Now according to Gauss divergence theorem, we can equate surface integral to volume integral. So double integral n bar dot f bar ds is equal to integral 0 to 1, integral minus 2 root x to 2 root x, integral 0 to 3 of divergence of f bar means 4 minus 4y plus 2z into dx dy dz. Now we have to just evaluate this integral. It will give you the value of surface integral which is given to us. So First, I will integrate this with respect to z. So that 4 has integration 4z minus 4yz and 2z has integration z square. Limits are 0 to 3. If you put only upper limit because lower limit is 0, so if you put upper limit, you will get this simplification 21 minus 12y. Now this is a function to be integrated. Now the limits are in terms of x. So first we will integrate it with respect to y. So 21 has integration 21y minus 12y has integration minus 6y square, and limits for y are minus 2 root x to plus 2 root x. If I put these limits, upper limit minus lower limit, I will get it as a 84 root x. I will get it as a 84 root x because 21 into 21, 22 root x you will get 22 into 2, 21 into 2, 42, 42 into again 2, 84. So it is 84 root x dx if you simplify it carefully, because upper limit and lower limit is similar, so it will be added 2 times. Therefore, now if I integrate this 84 root x with respect to x, and if I put limit 0 to 1, I will get the answer as 56 units, because this will be 2 into 84 divided by 3 into 1, and its simplification is 56. So this completes quickly what is the use of Gauss divergence theorem to evaluate surface integral with the help of volume integral. So I think you will understand this method if you learn it carefully, and if you just go through this video 2-3 times, and if you note that method, then certainly you will get this thing. Then we will go for the next example, that is example number 2 based on Gauss divergence theorem. So look at this example number 2. I will read that example. Evaluate surface integral f bar dot n bar ds by using Gauss divergence theorem, where f bar is equal to xi minus yj plus 2zk and s is the sphere x square plus y square plus z minus a square bracket square is equal to a square. Now as usual we will write first Gauss divergence theorem. Surface integral is equated to volume integral, and for that purpose what is required to find del dot f bar, divergence of f bar. So f bar is xi minus yj plus 2zk, and if you take this dot product of f bar with del, then dou x of x will be 1, dou y of y will be minus 1, and dou z of z will be 2. So this simplification comes out to be 2, and therefore surface integral f bar dot n bar ds will be equal to what? Volume integral 2 dv, because divergence of f bar is 2. 2 is out of this integral, and triple integral dv, where 2 into v. What is v? V is the volume of the sphere of radius a. V is the what? Volume of the sphere of radius a. Instead of evaluating the triple integral with the help of limits, it is very simple to solve in this way, because v is the volume of sphere of radius a. So volume of sphere is given by 4/3 pi r cube. R is here a, so it is 4/3 pi a cube. And if I put this v in this 2v, I will get, instead of 4/3, it will become 8/3 pi a cube. So this will be the final answer, where surface integral f bar dot n bar ds is evaluated with the help of Gauss divergence theorem for this region of surface of sphere. Is it okay? Now, after looking at this example number 2, now we'll go for the next example, that is example number 4. So look, example number 3 actually, and then we will come to the rest of that example. So look at this as the example number 3. Now we have to apply divergence theorem to evaluate surface integral 4xi minus 2y square j plus z square k dot ds bar over the surface bounded by x square plus y square equal to 4. Means this is circle and z equal to 0 and z equal to 3. Now if we look at this example, this surface integral we have to equate to a volume integral by using a Gauss divergence theorem. So I have done here. Look at this. Double surface integral n bar dot f bar ds is equal to volume integral del dot f bar dv. So we have to find what is f bar. It is given to you. It is 4xi minus 2y square j plus z square k. And now we have to find its divergence of f bar. It means we have to take del dot f bar. And if I take del dot f bar, I dot I1. So partial derivative of 4x with respect to x is 4. Then next term j dot z is 1. So partial derivative of minus 2y square with respect to y is minus 4y. And similarly, dou z of z square, because k dot k is 1, so we get its derivative as 2z. So divergence of f bar, what we get again? 4 minus 4y plus 2z. Now this divergence of f bar I can use to evaluate this volume integral. Before that, we will see for circle x square plus y square. If x square plus y square equal to 4 is a circle, then if I put y equal to 0, you will get x square equal to, if I put x equal to 0, you will get y square equal to 4. So, what will happen? I will get the value of, I will repeat once again. Here for this circle, if you look at this figure, for this circle, these are points on x-axis, minus 2, 0 and 2, 0, because this circle has center at origin and radius 2. So, along x-axis, x varies from minus 2 to plus 2. So, these are limits for x. And now we have to find limits for y along this strip. Is it okay? Because this strip will move from x equal to minus 2, x equal to plus 2. And along this strip, here is a y value and here is also y. This is y1 value, this is y2 value, say. So that if I simplify x square plus y square equal to 4 equation for y square will be 4 minus x square, hence y will be plus minus root of 4 minus x square. So y varies from minus root 4 minus x square to plus root 4 minus x square along the strip, and this strip will move along x-axis so that it will cover entire area of that circle. And z equal to 0 to z equal to 3 is already given in the example. So to evaluate the volume integral, we have limits for x, limits for y and limits for z also. Now according to this Gauss divergence theorem, I will write surface integral n bar dot f bar ds is equal to this surface integral, given surface integral 4xi minus 2y square j plus z square k into ds, which is a volume integral. And this volume integral equal to triple integral minus 2 to 2, these are limits for x, root of 4 minus x square to plus root of 4 minus x square, it is the limits for y, minus 4 to plus, and z equal to 0 to z equal to 3 are limits for z, and divergence of f bar is 4 minus 4y plus 2z dx dy dz. Now here also we will just integrate as seen in previous example. First integrate with respect to z, then put limits for z. If I put limits for z, I will get 21 minus 12y if I put limits for z. So it is 4z minus 4yz plus z square. If I put upper limit 4 into 3 9, 12 sorry, then here z square is 9, 12 plus 9 is 21, minus 4yz means 12y. Then if I integrate this term with respect to y, because we have to integrate with respect to y as the limits are in terms of x. So this is the order of integration. So if I integrate 21 minus 12y with respect to y, I will get 21y minus 6y square. And limits are minus root 4 minus x square to plus root 4 minus x square. And this is equal to, again, if I simplify, if I put upper limit, what will happen? 21 into root of 4 minus x square you will get, minus 6 into 4 minus x square, because this square root gets cancelled. Then whole this minus lower limit, if I put here y as negative value, it is again minus minus plus 21 root 4 minus x square, means 21 plus 21, 42 you will get root 4 minus x square. And for lower limit, this term is repeated with negative sign. So this term 6 into root of 4 minus x square. 6 into bracket 4 minus x square. This term will get cancelled while simplifying upper limit minus lower limit, and we get only this term 42 into root of 4 minus x square. Now this 42 is out of the integral. Now root 4 minus x square, this can be integrated with the help of the simple formula integration of root of a square minus x square. So what is that formula? I will write here. Look at this formula. Integration of root of a square minus x square dx. This is standard integration formula. It is equal to, I will write it as x by 2 root of a square minus x square, then plus a by 2. Is it okay? A by 2 root of a sine inverse x by 2. So this is the integral formula for root a square minus x square. This term is similar with that, root 4 minus x square. So it will be x by 2 as it is, 4 root of 4 minus x square plus 4 by 2 means a by 2, sine inverse of x by 2, limits are minus 2 to plus 2. If I put upper limit, what will happen? For upper limit, this 4 minus 4, upper limit, this term gets cancelled. As well as for lower limit also, this first term gets cancelled because it is 0. Only you have to simplify this term for upper limit. Means 4 by 2 is 2. Sine inverse 1 you will get, 2 by 2. Sine inverse 1 is pi by 2. So 2 into pi by 2 for upper limit. Minus lower limit, let this you will get similar, but here sine inverse of minus 1 you will get. So minus 2 into pi by 2. So minus minus plus, and we get answer as 2 pi by 2, 2 times, is it okay? 2 into pi by 2, and I will get it as 42 into 2, that is 84 pi by 2. Is it okay? This is 2 times pi by 2. 2 pi by 2, 2 pi by 2 means 2 times pi, sorry, not pi by 2, and we get as 84 pi. So this is the evaluation of surface integral with the help of what? Gauss divergence theorem. Now we have seen this 2-3 examples based on this Gauss divergence theorem in this lecture. Further examples, how to use this Gauss divergence theorem as well as how to verify Gauss divergence theorem, that we will see in the next lecture, because if that example is somewhat lengthy, verification of Gauss divergence theorem. So that we will complete in the next lecture. So today what we have completed, just I will repeat once again. First we have defined volume integral, and then after defining volume integral we have defined what is the, or we have stated What is the Gauss divergence theorem? So, quick revision I will take in this what we have completed as a lecture number 5. What is a volume integral? It is a if a continuous vector function f bar is defined in the region R bounded by some surfaces that I have shown a one figure to you, then the volume integral of f bar in the region is given by phi equal to triple integral f bar dv. F bar is this vector. How to evaluate multiple triple integral that we have seen already now. Now the Gauss divergence theorem we have defined. What is the Gauss divergence theorem? It gives relation between surface integral and volume integral. So we will define only that theorem. The statement of the theorem is the surface integral of the normal component means n bar dot f bar of a vector function over a closed surface S is equal to the volume integral means triple integral of the divergence of f bar means del dot f bar with respect to S. This integral you have to evaluate. So this surface integral and this is a volume of this figure. So the surface is bounded by this closed curve. Therefore, if I evaluate the surface integral, I will get the volume of this type of figure. So this lecture, I think you may get clear idea. You will get a clear idea, no doubt, about how to use Gauss divergence theorem and how to solve examples with the help of Gauss divergence theorem to evaluate the surface integrals by relating it with a volume integral. Thank you.